Just to say a few. Okay, it's working. Just to say a few words quickly about the outline of the presentation. I would like to say a few words about Wrocław, my university department, motivation, of course, which is obviously clear. And of course, I would like to speak a little bit about the dimensional analysis as a tool for predicting of fatigue crack growth models. However, I would like to put one line and of course to give you some consideration for the energy methods and of course the modeling of new generation elastoplastic models in fatigue crack growth rate. Of course, I come from Wrocław, and Wrocław is located in the southwest part of the Poland. This is my city, this wonderful city. This is the city of bridges and the dwarfs. We have more than 12 islands and of course 112 bridges, so we are called second Venice of the north. So we are in Italy, the Venice is the Venice, of course, but we have 5 rivers inside, and also it shaped me for analysis of the fatigue of bridges and of course fatigue crack growth rates. I remember my master thesis from it. As I said, we have very old bridges from 19th century, metallic bridges, and up to new modern bridges also, which are suffer for fatigue problems, and we need to calculate the fatigue is everywhere. So I don't want to say that Wrocław is the city of fatigue, but also of the bridges and dwarfs. Let's go to some interesting pictures from the city. This is the central point of the Wrocław Market Square, also Cathedral, University of Wrocław, one of the oldest in the city. We have 20 universities and also nice botanic garden. Okay. Few words about my university. Wrocław University of Science and Technology is one of the leading university, more or less 22,000 students, 5,000 the staff. Half of them is, of course, the staff of science. In doctoral school, we have more than 1,000 PhD students. It's one of the leading university, largest employer in Wrocław, and the second on the Lower Silesia district in Poland. Great facilities for organizing didactic process and also scientific meetings. Let's go maybe to my department very quickly. I am a head of the Department of Fatigue and Fracture in the Department of Mechanics and Material Science. We are interested mostly in various topics associated with the structural integrity, but mostly in fatigue fracture, so which is the topic of today's lectures. Just few pictures, well known, of course, multi-axial fatigue testing, some spring leaf testing under the fatigue. Maybe that will be more interesting because more or less everyone of us is involved in the fatigue and, of course, fracture. So this is also maybe not recent, but very interesting topic connected with the magnetic signals which comes from the fatigue process during the fatigue of specimens and materials for ferromagnetic materials, and of course for analysis. This is not from the finite element method, stress pattern, but this is the magnetic fields around the hole. And of course, in our labs we develop magnetovision camera, and we are able to capture magnetic fields. However, for involvement in the fracture mechanics, it's very tough by the language of the magnetic field and, of course, the mechanical field. Okay, let's go directly to the presentation, because I'm invited to speak not only about university, but about the stress ratio. Just 1 or 2 slides regarding the motivation. We remember Paris law and, of course, his great achievement by introducing the dependence between the crack growth rate and, of course, stress intensity factor. Of course, I think everything started from this expand. However, if we look for the models, which one we can select? I can prepare, I don't know, 10 next slides with some models, but which of the model is currently, let's say, the best? This is a competition still. I also wanted to just bring one famous thing from Albert Einstein. A theory can be proved by experiment. It's of course true, but no path leads from the experiment to the birth of the theory. It seems that in our case, it's exactly inverse. We started from the experiment, and Paris introduced the Paris law by observation of the experimental behavior of the cracks. Is it true? I think yes. If we look for the literature review, recently I found a great paper which order a lot of different scales and, of course, types and approaches. You can see just the next 5 generation of the models based on the strain, based maybe on the energy approach, based on linear elastic fracture mechanics, geometrical, plastic accumulation, of course, maybe dislocation-based, so micro-mechanical models. Which one is the best? This is still the question. And I guess that I am not able to answer today after the lecture, but maybe we can discuss about some direction. Of course, if you are talking with colleagues from aerospace industry, they love the NASGRO model. It works nice, of course. But if we consider the number of the constants which you need to estimate, it makes sense that only maybe for the richest companies like Airbus or Boeing that they are able to perform full-scale tests and also for different stress ratios. But still, this model is, let's say, empirical. Okay, let's go quickly to the main core of the presentation, dimensional analysis. Why I'm speaking about dimensional analysis and also the way from dimensional analysis to the crack growth modeling, it will be clear maybe in the next few slides. But I am pretty sure that every one of you remember, or maybe if it is new, I would like to present just a few important issues. Dimensional analysis is important in physics and also in modeling, especially colleagues from fluid mechanics, totally beneficial from this P. Buckingham theorem. You can see in 1914. So Sir Buckingham explained what exactly is it. So simply, this is fundamental theory of dimensional analysis, which means that if we have the n, let's say, parameters, so if we treat our experiment as a black box, and of course we see that we have n variables, k is the independent variables, we are able to build n minus k dimensionless products. That's more simple. How it works in the past, maybe this is not, we love the piece, but of course, I would like to show you something, let's say, spectacular. If you remember in 1945, when it was the nuclear in Trinidad, the explosion, people started to think, what is the dependence between the energy and, of course, the radius of the blast? Sounds like the challenge. In 1947, Taylor started to solve this equation by dimensional equation. And of course, I would like to show you how it works on a very simple example. So it is assumed that radius of the blast depends on 3 parameters: energy, of course, the density of the environment, and the time. So if we look for the process, we have 4 variables. So let's say, according to notation from Buckingham theorem, it's 4 variables, 3 dimensions. So which means that we are able to build 1-dimensionless products. Of course, we can express all quantities in the fundamental variables from the physics. And of course, after selecting the A, T, and rho as repetitive variables, we can build that P1 is R times energy to the A, T to the B, and rho to the C. And after the simple solution, it is called in the theory of the dimensional analysis like Rayleigh's methods. It's very simple, so exponent methods. We can solve very simple equation and found C, A, and B exponents. So therefore, we have P1, which is, of course, the physically consistent with the dimension. And, of course, if it should satisfy the equation of fundamental dimensional analysis, it seems that P1 must be constant. So we have the simple dependence for the blast radius. And finally, if we have this, of course, we need experiment. This is not we do the experiment. Therefore, by observation of the expanding from the photographs blast radius, we are able to calculate by solving the equation what is the energy. Of course, it is more or less true and close to the pure value what was used during this trial. Maybe it's not nice example because it's on the nuclear bomb, but of course, it's in physics, especially in hydraulic system, there is a lot of examples of successfully implementation of the dimensional analysis, Reynolds number, Mach number, Freud number, a lot of invariants. Why not in fracture mechanics? And when I started to prepare for my presentation, of course, I made a sentimental excursion to the heart of dimensional analysis. There is not many papers regarding the dimensional analysis and fatigue crack growth model in the same sense, of course, like in the physics. However, if you look to in Google Scholar or maybe different database, we can easily capture that there is few important Italian scientists like Alberto Carpinteri and of course Ciavarella and Paggi that they did a lot of the jobs and efforts. Of course, based earlier because in 1980 I found the paper from Barenblatt and Botfina. Barenblatt is of course working in University of Stanford and Botfina in Moscow. They started to, let's say, capture the fatigue crack growth rate based on this. The idea is not so simple as previous example, of course, because we have many variables in the fatigue crack growth, but maybe this lecture can explain us what is the meaning of C and M. And also in the paper of Ciavarella, Paggi, and Carpinteri, they explain it a lot, what is the dependence between the M and C, and if are independent or not. I don't want to speak about it, but just show you the way. Okay, let's assume that fatigue crack growth rate according to our experimental observation. This is the main conclusion, which will be underlined on the final. Dimensional analysis did not substitute our experimental observation. So we have the yield strength, K1C, of course, frequency of loading, delta K threshold, of course, the fatigue limit, Young modulus, and some microstructural or maybe scale effects, and also stress ratio, which is, of course, a still redundant parameter in the fatigue crack growth description. So they built 7 dimensionless products, and of course, you can see Paris law looks like this. But in the dimensional analysis theory, we are speaking about self-similarity, if it is complete or incomplete. It is crucial point if we satisfy both equations, so the limits of the, you can see, dimensionless products. If we, for instance, would like to treat any variable as a maybe non-essential, we need to find for the limit which, for instance, P1 tends to 0 or infinity, so for small or for very large numbers, this limit should be, let's say, non-zero. You can see, for instance, for P1, which is, of course, delta K referred to K1C, which obviously very nice explain dimensionless system. You can see, for instance, this is P1, delta K referred to the K1C. You can see that for value lowest to the 0, it's infinite, and also on the second hand, we have the second asymptotic. So we are talking that delta K is it essential for description of fatigue crack growth rate. Therefore, you can see it comes from this to this region, then we can have delta K in the exponent B. Only in these terms, we can explain that if delta K is close to 0 or infinity, the equation tends to the 0 or infinity. Okay, maybe let's accelerate a little bit. So this is a great job done by colleagues from Italy. And of course, they used fundamental theorem of the dimensional analysis, and independently, they demonstrated that this approach efficiently allow us to build different type of the models. Of course, we know this group of the models from the literature. So you can find some proposal by Ricci, by Klesny, Lucas, but many various other scientists from the Czech Republic, also from Poland. But the key question is, if we make one step more, what will be the next generation? Initially, I started my let's say, adventure with the fracture mechanics with, of course, with energy approach. And I have a lot of confusion at the beginning, because if we try to involve the energy approach, you can see, for instance, the old papers of Fine and Davidson, and they measured the energy ahead of the crack tip, or maybe other paper by different researchers they have, you can see, Klingberg, and also different models with the energy We can obtain also the correlation between the dissipated energy versus number of cycles, so let's say crack growth rate. And also in the recent papers, we are now living in the new domain. I don't want to say anything about the AI, but of course it could be also useful in this regime. But if we split the numerical experimental full field analysis in front of the crack tip, the conclusion from all works more or less was similar like from the dimensional analysis, that crack growth process must be dependent from two parameters. And also in our labs, we started many years ago, was initiated by my mentor, Professor Shata, energy balance for the infinite plate. Just quickly, on the left side, based on the first principle of thermodynamics, we have the external work, heat, and also strain energy density, kinetic energy, and also damage energy. Simple balance from the physics. Sounds very easy, but if we skip the heat energy, treating as an adiabatic process the crack growth, and also kinetic energy for, let's say, relatively low frequencies of the loading, we are able to build the energy balance after differentiating over the number of cycles, and we can more or less build the idea of the generalized crack growth, in this case, surface of the crack growth. Also, for this purpose, we are able to use detailed investigations from classical fracture mechanics three-field models, or maybe different. In this case, was Dugdale-Panasiuk models, and of course, all displacement in the vicinity of the crack tip allow us to calculate some components. After simplification, we can share with you our papers. And finally, it is something like this. So we can introduce new energy parameter, which is based on the dissipated energy in each cycle of loading. And of course, B, it's the thickness of the specimen, and as well as K1 max. So it is, let's say, trace of the loading, and of course, critical stress intensity factor. Moreover, this, let's say, phenomenological way can be also solved in different way. In our case, we also, many years ago, after the ACF, last time also in the paper with Professor Berto, we tested old steels. And also we would like to remind in this paper an excellent way, which was done a few years ago for finding the same, let's say, crack driving force from the dimensional analysis. However, in this case, it was not easy to use only simple P. Buckingham theory, but we used the, let's say, novel theory, which comes from the geometric methods of the analysis, dimensional analysis. And maybe just to move to the next slide, also the same results can be confined. As you can see, based on the energy approach, of course, we have one line for two stress ratio, which is, of course, obviously the main beneficial effect. And also, what is important, the energy parameter overcomes all, let's say, disadvantages of the linear elastic fracture mechanics limitation. Finally, I would like to show you maybe the last, but not least, parameter which we tried to solve also by combining and maybe translating the idea of new generation of the models from dimensional analysis to delta S star, which is combination of course, well-known cyclic J integrals. And it works like this. So we have the delta J regime and J max. And we tested, in our labs, few types of the materials. In this case was 3 types of the materials. So I'm controlling the time. So it was the steel from the energy sector, 12 HMF, also S355, 41 chromium 4 steel with different hardness level. Yeah, I'm approaching the results, measuring the energy, and of course, just very quick view to the results. We can see that for this case, for 2 stress ratios, we have 2 lines, and if we use the energy parameters, we have 1 line. Of course, the same for chromium steel, 41 is here 4 steel, 3 different stress ratio, and 1 line for all stress ratio. The same again for different quenched and tempering for this steel, for S355, 4 stress ratio, and 1 line. So I will quick also to the final conclusion for mode 1 test, also for different stress ratio. However, if we plot in the delta J, so let's say cyclic J integral, it is not in resultant to decrease the effect of stress ratio. However, if we use the energy parameter, it's also okay. Just very quick to conclusions. For mixed mode, we also recently started to test also under the mixed mode. As we know, mixed mode, we can also translate for equivalent stress intensity factor, and the values is the last slide of my presentation. We have the same effect for mixed mode. For P355, NR1 still so similar to S355 with the fine coursing. Conclusions, just to finish. The main conclusion is that the dimensional analysis cannot replace experimentator and, of course, our knowledge from the fracture mechanics, but it is a good direction for finding new type of the models. Thank you for your attention.